Good morning, students. Class 10, Chapter Light. Today, 9 April, we will discuss you through Diksha rules of image formation by concave mirrors in detail. So, you should watch it carefully, listen carefully, and make diagrams with pencil and scale on your copy. Prepare fair notes. So, let's start.
Shows the image which are formed by a concave mirror. Now, in ray diagrams, we actually study that if you are changing the position of the object, how is the nature and the position of the image is changing. That is the importance of a ray diagram. And why do we study the rules? Because to make the ray diagrams, it's important to study the rules. If you know the rules, you will be able to make the ray diagrams very easily. So let's go through all the image formation by a concave mirror one by one. So the first one, we can see that AB actually represents the object and the object is at infinity. So there is an object at infinity. A practical example, let's say you have a concave mirror and there are rays coming from the sun. The sun is located at infinity, right? So whenever the rays from the object which is at infinity strike the mirror, they all are the parallel rays. They are going to hit the reflecting surface of a concave mirror. And as per the first law that we have studied, rays which are parallel to the principal axis are going to meet at the focus. So that is what is there in the first ray diagram. The rays which are parallel coming from the object at infinity are going to reflect back and meet at a point which is known as the focus. Now what we have done, we have shifted the object closer to the mirror. So now, we have the object closer, it's beyond C now. It's not at infinity, now we have shifted it closer to the mirror and now our object is beyond C. Now in the first ray diagram, when the object is at infinity, the image you can see is formed at the focus. We can look at the size of the image, it is point size, and the nature of the image is real, right? Because the rays are actually meeting, so it's a real image. So real and inverted is going to be the nature of the image. Now for every ray diagram that you're going to study, you need to know these 4 points. What is the object position? What is the image position? What is the size of the image? And what is the nature of the image? Moving on to the second ray diagram, the object is beyond C. Now when the object is beyond C, as you can see, the image is formed between the focus and the center of curvature. Now here, the size of the image is smaller than the size of the object, and the image formed is real and inverted. Now how can we say that the image is real and inverted? Because it is formed below the principal axis. Moving on to the third ray diagram, the object is at C. So now we have shifted the object closer to the mirror and now our object is at the center of curvature. So when we apply the laws, so what laws have we applied in the third ray diagram? A ray that is going parallel to the principal axis is passing through the focus, and a ray that is passing through the focus is going parallel to the principal axis. Now here you can see that the image is formed at C. So the object is at center of curvature and the image is also formed at the center of curvature. What is the size of the image? The image is of the same size as the object and the image is real and inverted. Why real and inverted? Because as we can see, the image is formed below the principal axis. So it's inverted and real. Moving on to the next ray diagram, the fourth one, which is the D part here, we have shifted the object further closer to the mirror. So now the object is between C and F, right? So now as per the laws and as per the rules that we have studied earlier, we can see that the image is formed behind the center of curvature. And if you carefully look at the size of the image, it is bigger than the size of the object, right? So that is why the size of the image is enlarged and it is real and inverted. For the next ray diagram, we have shifted the object further close to the mirror. Now our object is at the focus. So the image is formed at infinity and it is highly enlarged in size and the nature is again real and inverted. And for the last ray diagram, here the nature of the image changes. Now when the object is very close to the mirror, that is, you can see the position of the object, it is between F and P. So when the object is very close to the mirror, the image is formed behind the mirror. That means that the nature of the image which is formed is virtual and erect. How can you identify that the image is virtual and erect? See if the image is formed below the principal axis or if the image is formed above the principal axis. If you carefully look at this ray diagram, the image is formed above the principal axis. So it is virtual and erect. Size, as we can see, is enlarged and the image is behind the mirror. So this is the only case in a concave mirror where the image formed is virtual, erect and enlarged. For all the 5 cases, you can see here that the image formed is real and inverted. Now this is the table which is actually showing the object position, image position, size of the image and nature of the image, which we have already discussed. Now this was the image formation by a concave mirror. We now move on to a convex mirror. So these are the 2 ray diagrams which we are going to study for a convex mirror. First ray diagram, as we can see, what is the position of the object? The object is at infinity. Now again, practically you can imagine that, let's say this object is sun and sun is situated at infinity. There are parallel rays falling from the sun onto the reflecting surface of a convex mirror. What is the convex mirror going to do? It acts as a diverging mirror, so it's going to diverge all the rays, right? But these rays are going to meet virtually at a point which is known as a focus. So this is the first ray diagram where the object is at infinity, image is formed at the focus and the focus is situated behind the mirror. And what is the size of the image? The size of the image is highly diminished, its point size, and the nature of the image is virtual and erect. The second one is the position of the object is between infinity and the pole. So on applying the rules which we have previously studied, we see that the position of the image is between P and F, which is behind the mirror. Image size is smaller than the size of the object. So that is why we have written that the size of the image is diminished. And since the image is formed above the principal axis, it is virtual and erect. So these are the image formations by a convex mirror. Now what are the practical uses of concave and convex mirrors in our day-to-day lives? First, let's look at the uses of concave mirror. Now concave mirrors are used in the torches. So the reflector of the torches, these are concave in shape. And searchlights, headlights, they also use concave mirrors. After that, they are also used as shaving mirrors to see larger image of the face. Then they are used by dentists to see larger images of the teeth. And large concave mirrors are used to concentrate sunlight to produce heat in the solar furnaces, because we have studied these are converging mirrors. So these are some day-to-day uses of concave mirrors. Moving on to the uses of convex mirrors. The major use of convex mirrors that are its use as a rear view mirror in the vehicles. And convex mirrors give erect, diminished images of objects, so they also have a wider field of view than plane mirrors. Now, that is the sole reason why we use convex mirrors as a rear view mirrors. So, it actually forms a smaller image, so it covers a larger area. So, it gives a wider field of view to us. Now, you must have observed these kind of mirrors also in the supermarkets. Now, these are also convex mirrors. Now these are also used for security or surveillance purposes in supermarkets. You might have also noticed these kind of mirrors at metro stations, in the parking areas. All these kind of mirrors are convex mirrors. Because they form small images, virtual images of the object, they cover a large area. They give a wider field of view, which is the main reason why these are used for security and surveillance. Now there are certain sign conventions which we are going to follow for the spherical mirrors. Whenever we take the object towards the object or any distance which is towards the left, we take it as negative. All the distances that we take towards the right side of the mirror are taken as positive. So if we go through the points here, the object is always placed on the left of the mirror and light from the object falls from left to right, right? And all the distances which are parallel to the principal axis are measured from the pole. All the distances which are measured to the right are taken as positive. All the distances measured to the left of the pole are taken as negative. Whatever are the heights that we measure above the principal axis are taken as positive. Heights which are taken below the principal axis or downwards the principal axis are taken as negative. Now we will be studying about one formula which is known as a mirror formula. This is the mirror formula which is given by 1 upon V plus 1 upon U equal to 1 upon F. Let's see what all these terms mean. Now V is actually the distance of the image from the mirror. U is the distance of the object from the mirror and F represents the focal length. So if you're taking the distances on the left side, you will be taking it as negative. If you're taking the distances on the right side, you will be taking it as positive. And these are the sign conventions which you are going to follow when you're solving the numericals. Now, this is a mirror formula, and after which we have also a formula for magnification. What does the magnification represent? Magnification for spherical mirrors is ratio of the height of the image to the height of the object. So this ratio, height of the image, height of the object, is actually defined as magnification, right? The magnification is also related to the object distance and the image distance. That means that for magnification we have two formulas. One is in terms of height, image distance divided by the object height, and then we can also represent it in forms of distances, which is minus V by U. So the first formula is height of the image divided by the height of the object, and the second formula is negative of image distance divided by the object distance. So these are the two formulas which are related to magnification.
Thanks for watching.